Hello and welcome to the channel. This task is found somewhere at HackerRank site. Unfortunately, I can't give you neither the link to the task nor the exact formulation of it. In essence, it is about the following. Given a sequence of n random numbers, a0, a1, etc. until a with index n-1, it is required to find a subsequence a from index j to index k inclusive, so that the sum of its elements taken with alternating signs, plus then minus, then plus again and so on, is the biggest. In particular, j can be equal to k, so that the subsequence has only one element and its sum is just this element. Or on the contrary, the subsequence can match the whole sequence, in which case j is 0 and k is n-1. Take for example the sequence 1, 2, 3, 4, 3, 2, 1. 4 is the maximum element. If it is taken alone as a single element sequence, the sum is 4. If we take it with the next element, we get 4 minus 3, which is 1. While taking it with the previous element gives the sum 3 minus 4, which is negative 1. We can try a 3-element subsequence 4, 3, 2, in which case the result is 4 minus 3 plus 2, which is 3. This is still not enough to beat the singleton value of 4. A 4-element subsequence 4, 3, 2, 1 gives the result 2, which is even less. In the similar way, we can try all other subsequences and find out that the subsequence consisting of only 4 gives the maximum sum. Since the element 4 has index 3 starting from 0, the answer is j equals k equals 3. And the biggest sum is 4. Now let's exchange elements with indices 4 and 5. So the new sequence is 1, 2, 3, 4, 2, 3, 1. In this case, the base value is 5 and is obtained by subsequence 4 to 3, corresponding to indices from 3 to 5. So j equals 3, k equals 5, and the value is 5. As an exercise, try to find the answer for sequence 7 to 1, 7, 4, 5, 1. The best value is 9 and obtained by the subsequence with indices from 1 up to 5. It may happen that several subsequences give the maximum value. In this case, the algorithm presented in this video will bring the subsequence with the least starting index. In the description under the video, you will find the links to 3 projects: Xcode project with Swift and C implementations, C-only project for Microsoft Visual Studio and Microsoft C, which unfortunately isn't POSIX compatible, as well as generic C project to be built with GCC and its clones like MinGW. There are Swift distributions for Windows and Linux Ubuntu, however I never tried them, so I bring my apologies. To start, let's simplify the assignment by considering what I call the light task. The difference is that here we have only pluses, so each element is taken with its own sign, which can be either positive or negative. I suggest you to pause the video and think of the ways to implement the algorithm. If you start thinking about the algorithm, the first that comes into mind is what I call the dumb algorithm. Look up all subsequences and find the one giving the maximum sum. To make it clear, let's create a table. The left column will show the starting or the lowest index from 0 up to n-1. The middle column will show all the subsequences starting with corresponding index. The right column will show the number of such subsequences. For starting index 0 we have a singleton containing just a0, a 2-element subsequence of a0 and a1, a 3-element subsequence from a0 up to a2, and so on, until we finally get to the whole sequence containing n elements. So the number of subsequences starting with index 0 is n, for starting index 1. Again we have a singleton, this time it contains a1, and a two-elemented sequence of a1 and a2, and a three-elemented sequence from a1 up to a3, and so on. The last term here is the subsequence from a1 to a with index n-1, consisting of n-1 elements. Element a0 does not participate here, so there are n-1 subsequences starting with index 1. And we proceed to index 2, where there are n-2 subsequences from a singleton containing a2 up to n-2 elemented subsequence. And we continue filling the table until we get to its last row, corresponding to the starting index n-1. This row has only one subsequence, a singleton containing a with index n-1. We see that the total amount of subsequences is the sum of first n natural numbers. I hope you haven't forgotten that the value of the sum is n times n plus 1 divided by 2. And this is the total number of iterations the DAM algorithm is going to have. Also we see that the DAM algorithm needs two loops. The outer loop by starting, or we can say it lower index, from 0 to n-1, and the inner loop by the upper index in the range from the lower index up to n-1. And this is my implementation of the DAM algorithm EC for the light task. I prefer to deal with integer data to avoid possible inaccuracy. So by default the code uses long data type, which guarantees to be at least 64-bit long according to C99 specification. However, you may define C preprocessor macro float data, in which case double precision floating point data is used instead. For returning the result, there is algorithm result structure defined in the header file algorithm.h. It contains the lower and upper indices as well as the sum of the evaluated subsequence. Now let's look at the function named DAMLight. The sequence is passed as an array. The length of the sequence for C is specified explicitly as the second argument. The last argument is the pointer to the field where the result should be placed. The function returns 0 on success and 8 on failure. Quite obviously the sequence must be non-empty, otherwise there is an error. Then we initialize the best sum and the best indices. -1s for the indices are needed just to avoid warnings. However, the initialization of the sum is important. Since we are looking for the maximum value of the sum, we initialize it with the minimum value of the selected data type, which is -infinity for the floating point data or the lowest possible number for integer data. And here is the outer loop by the lower index, number j, and the inner loop by the upper index, number k. We keep a variable named running sum, which is initialized to 0 before starting the inner loop, and within the loop it accumulates the value of the subsequence. So we get the value of the singleton, then the value of the two-elemented subsequence, three-elemented subsequence, and so on. And if the sum exceeds the best value, we update the best value and the indices. At the end of the outer loop, we check that the indices are set, which is actually redundant, fill the algorithm result field with the best indices and the best value, and return 0 to indicate success. Now to Swift. Quite honestly, I am not a fan of this language, as it has a number of features I am, softly speaking, not impressed with. However, for this task, especially for the DAM algorithm, Swift is just perfect, so I couldn't avoid the temptation to use it. The first Swift feature we are going to use here is the ranges. Instead of having separately lower and upper indices, we can keep them as a range. The second feature is array slices or subarrays, which is different from, for example, copy of range in Java, as Swift doesn't actually copy the array, but creates a view onto it. The third feature is enumerated method for an array that allows to have indexed an element without keeping an additional variable. And the fourth feature that I desperately want to see in Java for many years, but it will probably never come to it: preprocessor macros called compilation conditions in Swift. So again, we can select the type of data, depending on whether or not compilation condition float data is defined. This time, algorithm result is a tuple containing just two elements, the range and the sum. Now our function has only one argument, which is the sequence. The length of the sequence doesn't need to be specified explicitly, as it can be found using count property. As about the algorithm result, it is returned as an optional value, with nil returned on error. Instead of checking the count, I could check isEmpty property, but since I need count for another purpose, I use it for free. This time we need only two variables to keep the result, which are best value and best range. The outer loop still runs by index from 0 up to sequence length -1. And again we have running sum. However, this time the inner loop runs not by an index, but by an array slice, from the lower index up to the end of the sequence. The slice is used with enumerated, which creates an array of tuples, each containing two fields: element for the element in the array and offset for the index in the array slice. However, instead of index in the array slice, we need the index in the whole sequence. Therefore, when updating the best range, we add the lower index to the index in array slice. After the outer loop is complete, we check if the best range is set, and if it is, we return the algorithm result with the range and the best sum. Otherwise, we print the error message and return nil. After all, the dumb algorithm has a good feature. It is simple and straightforward, therefore it can be trusted. So we will use it for testing the optimized algorithm, which is too tricky to be trusted. Let's see how we can optimize the algorithm. Let S with index I be the sum of first I elements in the sequence. So S0 is 0, while for a positive I, Si is the sum of elements from A0 up to A with index I-1. What we really need is the sum of subsequence starting with an arbitrary index j. Let's add to this sum the sum of starting j elements. And of course we need to subtract the added sum, since we don't want the value to change. It can be easily seen that the starting k+1 terms give S with index k+1, while the subtracted sum is S with index j. Therefore, the sum of subsequence starting with index j and ending with index k is S with index k+1 minus S with index j. This equation shows that for a given upper index k, the maximum sum is obtained with lower index j giving the minimum value of Sj. This suggests the following algorithm. For which k from 0 up to n-1, find the index jk no more than k, giving the minimum value of S. This minimum value we denote with Lk. According to the obtained formula, the difference dk between S with index k+1 and Lk is the sum of subsequence starting with index jk and ending with index k. But jk gives the minimum value of S. Therefore, dk is the maximum sum of all subsequences ending with index k. What remains to do is taking the maximum of all decays. This maximum will be the best sum. The corresponding k will give the upper index for the best sum range, while the lower index of it will be j of the corresponding k. The smart part about it is that it can be done in a single loop, which evaluates both lk and dk. Therefore, instead of n times n plus 1 divided by 2 iterations, we have now only n iterations, which is n plus 1 divided by 2 times less. Of course, since each iteration has become more complex, the actual gain in time is less than z. However, it is still significant, especially with a big amount of data. And here is the implementation of the optimized algorithm in C. The code has become bigger, but it is expected to be more efficient. For convenience, I copied here the formula for the optimized algorithm, and let's see how it is actually implemented. Still we have best from index, best to index, and best value. Now best value is the maximum of all decay found so far. At start it is again the minimum value in the type, and it updates each time when the new value of decay is more than its own value. Best to index is the index k giving the maximum value of decay. Best from index is the value of jk for the best to index. I remind you that jk is the index not exceeding k giving the minimum value of s. It corresponds to the maximum sum of all subsequences ending at index k. Now we have only one loop and a single index in the loop, running from 0 up to the length of the sequence minus 1. And again we have a running sum, which is the sum of sequence elements processed so far. At start, the value of running sum is 0, which corresponds to S0. Then we add element 0 of the sequence, so the value of running sum becomes equal to S1. In the next iteration, we add element 1 of the sequence, and the value of running sum becomes S2. Every time after the addition, the value of running sum becomes equal to S with index 1 more than the current index, and this shift needs to be taken into the account. Finally, we have two new variables missing in the DAM algorithm. Current from value, named LK in the description of the algorithm. This is the minimum of all running sums processed so far, and current from index, named JK in the description of the algorithm. This is the index corresponding to the minimum running sum. At start, the current from value is 0, corresponding to S0, and the current from index is 0 accordingly. Current from value and current from index are updated each time when the running sum is less than current from value. Now the loop has two operations. The first operation is updating the best value and the corresponding range, which is similar to what we have in the DAM algorithm. This time we find the new value dk by subtracting the minimum running sum from the current running sum. Note that in the formula we have s with index k plus 1. However, since the index of the running sum is shifted, everything is alright. And if the new value exceeds the best values found so far, we update the best value and the range for it. The second operation in the loop is updating the current from value, which is the minimum running sum, and the corresponding index. So, if the current running sum is less than the current from value, we update the current from value and the current from index, where because of the shift in the index of running sum, we have to add 1 to the current index. It should be noted that updating the base value should take place before updating the current from value, to ensure that the old current from value is used for calculating the new value. This observation is essential when both updates take place in the same iteration. Such a simultaneous update will happen in the very first iteration of the loop in case the starting element of the sequence is negative. But may a simultaneous update take place after that? In other words, if I take the iteration for index 0 out of the loop and start the loop from index 1, can I place else between the operations? This allows to skip comparing running sum if the base value was updated. The feeling is that it actually can be done. But firstly, this is just a feeling that needs to be proven. Secondly, this increases the code, so I can hardly fit it into a page. Thirdly, it practically doesn't save the time, if it saves at all. So I'll better keep the code unchanged. The end of the function is practically the same as for the dumb algorithm, as this 50 permutation of the optimized algorithm. Here we use best range instead of two indices and enumerated for the sequence, making both element and its index available. But we don't have the inner loop, so we don't use array slices. Someone may find this code pretty boring because of the absence of anonymous functions. The following code may satisfy such viewers. It uses reduce instead of a loop, and there is a tuple named running data keeping the current status passed from one invocation of reduced to another. The final status is returned and the best range is retrieved from it. If the best range is set, the algorithm result is created and returned, otherwise there is an error message and the function returns nil. The appearance of the code has changed, but the code hasn't changed essentially, only it has become bigger and more engaged because of the need to pass the status. Has it become more readable? I doubt. To me, the code with an explicit loop looks much neater. In fact, I like lambda functions only if we use them in the code, however this time it simply doesn't serve the purpose of making the code clearer and more efficient. Therefore, in the project you will find this code commented out in favor of the original one with an explicit loop. And to the real stuff, what I call the full task. As you hopefully remember, in the actual task from Hacker's Rank, the signs are alternating, plus minus, etc. And again I suggest you to think about implementing the algorithm before proceeding. For the dumb algorithm, the sign alternation doesn't make a big difference. We just add a variable named factor, which is 1 for the even elements of the selected subsequence and -1 for the odd elements. At start of the inner loop, the factor is set to 1, and during each iteration of the inner loop, it changes the value to the opposite. Now, before being added to the running sum, the element of the subsequence is multiplied by the current factor. Someone may argue that instead of keeping the factor as a separate variable, I could get it out of the subsequence index. However, this way looks to me more readable and probably more efficient. The similar changes applied to the Swift implementation. You can find the corresponding Swift code in the project. So let's move on to the optimized algorithm. Now, instead of Si, we have Pi, the sum of first I elements of the sequence with alternating signs. So P with index 0 is 0, while for a positive I, we have a sum where elements with even indices appear positive, while the elements with odd indices appear negative. This is the same as multiplying each element by -1 to the power of its index. particular, the last element in the expression for pi has index I-1 and appears with factor -1 to the power of I-1. Now consider a subsequence starting with index j and ending with index k. The last element of the subsequence has a relative index k minus j from the start of the subsequence, therefore it appears multiplied by -1 to the power of k minus j. Let's, similarly to what we did for the light task, add and subtract the alternating sum of starting j elements of the sequence. We can see that if j is an odd number, the last added element a with index j minus 1 appears positive, while the following term aj is also positive. Two positive elements in a row is certainly not what we need, therefore the method needs to be improved. The solution is multiplying the added elements by -1 to the power of j, and we need to subtract them to keep the expression unchanged. Now, after we expand the brackets, the factor for a with index j minus 1 is -1 to the power of 2j minus 1. Since 2j minus 1 is always an odd number, this term will be certainly negative, so there will be no consecutive positive terms. Now, from the first k plus 1 terms, we can factor out -1 to the power of j. The expression in square brackets is p with index k plus 1, and it is multiplied by -1 to the power of j. The subtracted term is -1 to the power of j times p with index j. Finally, the alternating sum of the subsequence is -1 to the power of j times p with index k plus 1 minus p with index j. Presence of factor -1 to the power of j means that the difference p with index k plus 1 minus pj has to be maximized for even j and minimized for odd j. In order to achieve that, I could find nothing better than keeping two sets of jk and lk. Theoretically, the optimized algorithm looks as the following. For any k from 0 up to n-1, find jk even, giving the minimum value of pi for even I not exceeding k. Let lk even stand for this minimum value. Evaluate dk even as p with index k plus 1 minus lk even. Find jk odd, giving the maximum value of pi for all odd I not exceeding k. Call this maximum value lk odd. Find dk odd as minus p with index k plus 1 plus lk odd. Let dk be the maximum of dk even and dk odd, and jk be either jk even or jk odd, depending on whether dk even or dk odd is taken for dk. The rest goes just like for the light task. We find k best, giving the maximum value of dk for all k. This maximum value of dk will be the best sum. K best is the upper index of the range, and the lower index is j for k best. However, there is something I don't like here. Taking minimum for jk even and maximum for jk odd would make the code a bit awkward and reduce its readability. Can we have a minimum all the time, as we had for the light task? We can do that by keeping lk odd with the opposite sign. So we write instead that lk odd is minimum of negative pi for all odd I not exceeding k. Consequently, we need to change the sign for lk odd in the formula for dk odd. And we get dk odd equals minus p with index k plus 1 minus lk odd. So in both cases, the value of lk is subtracted and only the sign of p with the index k plus 1 changes. Now we are ready to implement the algorithm. This is the implementation of the optimized algorithm in C. Again, we have familiar fields, best value, which is the maximum value of decay found so far, and the range from best from index to best to index corresponding to the best value, and the running sum and the factor similar to what we had for the DAM algorithm. The loop with index from 0 up to sequence length -1. At start, the running sum is 0 corresponding to P0 and the factor is 1. In the loop, we add to the running sum current element of the sequence multiplied by the factor. This makes running sum equal to P with the following index. So again there is a shifted index as in case of light task. After that, the value of factor is changed to its opposite. All that we've seen previously, let's see what we have new. According to the algorithm, we need to keep two values of jk and two values of lk for even and odd indices. That's why current from value and current from index have become two-elemented arrays, where element 0 corresponds to even data and element 1 to odd data. And variable parity index keeps currently used index of these arrays 0 or 1. According to the algorithm, for each k there are two dk, dk even and dk odd, and each of these has to be compared with the best value. This is done in the inner loop. At start, when current index is 0, there is no need for dk odd, since the odd elements haven't come yet. This brings up another variable, parity index max, which is originally set to 0, then increased to 1 in the loop. Let's see how the inner loop works. We can see that for dk even, the running sum is taken with plus, while for dk odd, it is taken with minus. Therefore, we have a variable named active running sum, which before the inner loop is set to the running sum, and inside the loop it changes to the opposite value. And we take the difference between the running sum and corresponding lk, even or odd, and compare it with the best value. And if the evaluated value exceeds the best value, we update the best value and the range. So we actually do have an inner loop here. However, it has no more than 2 iterations. Someone who really wants to have a single loop can get rid of the inner loop by duplicating the statement separately for even and odd parity indices. However, I like reusing parts of the code, which makes it neater and shorter. The remaining statements of the outer loop deal with maintaining current from values and current from indices, lks and gks, in the description of the algorithm. Here, the parity of processed data should match the parity of running sum, whose index is one more than the current index. This means that the parity needs to be changed to the opposite. For that reason, the factor is changed to the opposite not at the end of the outer loop, as seems logical, but earlier, before starting dealing with current from value and current from index. For the similar reason, the index of the outer loop is changed not at the end of the loop, but right here, before getting the parity index. This makes factor and the parity index consistent, and we can proceed. I bring my apologies to the supporters of disciplinary programming, but this time it was so irresistible that I just couldn't help it. Since we have agreed to keep lk odd with opposite sign, the running sum is multiplied by a factor. This will keep running sum for even indices and change it to the opposite for the odd indices, just what we need. As the inner loop is complete, active running sum variable can be reused, which may be also against the discipline, but since I debated once, why can't I do it again? So we compare active running sum with the corresponding current from value, and if the new value is less, we update the current from value and current from index. Note that since the loop index is already incremented, there is no need to add 1, as we did for the light task algorithm. Another observation. At start, current from value for even indexes is set to 0, which corresponds to P0. However, for the odd indices, the current from value remains undefined until we process the starting member of the sequence. Therefore, we initialize it with data max, which is plus infinity for floating point data and long max for integer 64-bit data. As start, the loop index is 0. After incrementing, it becomes 1, and parity index will be also 1. This means that active running sum is compared with data max. Such a comparison will certainly hold, so current from value and current from index will be properly set. Meanwhile, parity index max is set to 1, and it will stay equal to 1, so from now on the inner loop will have 2 iterations instead of 1. The final statements are merely the replica from the previous code. Swift implementation uses sequence enumerated for the outer loop, so the loop index isn't maintained explicitly, and we need to add 1 in assigning current from index. The parity index is set to 0 start, and inside the loop it is exclusively ORed with 1. This makes it alternate between 0 and 1. Note the Swift 2 and above treats a loop variable differently from C. Here, parity index in the inner loop is a different variable, living only inside the loop. And of course we use best range instead of best from index and best to index. Everything else is similar to C implementation. Now let's take a brief look at the main module. At start, it processes command line arguments. Before calling the algorithm, it generates a random sequence and prints it if necessary. After running each algorithm, it records the duration. Then it checks and compares the results, print results, durations and errors, if any. We will look at the Swift implementation of the main module, which I believe is easier to understand even to someone who is not familiar with Swift. While C implementation is designed to run in different environments, such as Xcode, Visual Studio, or just built with Make, the Swift main module will compile only in Xcode because of using specific Xcode and macOS features. This makes it much simpler to understand. To process command line arguments, I use getOpt, which is actually a sim function, but it is accessible from Swift in Xcode. The arguments are the following. S is the number of elements in a generated sequence, 100 elements by default. B is what I call bit capacity, number of bits used to represent each element of a sequence. By default, the bit capacity is 8, which corresponds to the range -128 up to +127, if positive only is off, or from 1 up to 255, if positive only is on. The maximum allowed value of B for integer data is 56, which is 8 less than the full bit capacity of 64. This is done in order to reduce the risk of overflow, given that, as you probably noticed, the algorithm implementations assume that overflow never happens. At the same time, this ensures that all sequence elements are strictly more than data min and strictly less than data max, which is important for the algorithms to run correctly. parameter b is unavailable for floating point data, in which case the elements are always generated in the range from 0 to 1 if positive only is on, or in the range from -1 to 1 if positive only is off. Argument r sets the number of runs, 5 by default. For each run, a new sequence will be generated. Argument v allows to enter specific values instead of using generated one. In this case, arguments s, b, r, and p are ignored, and there will be only single run. Argument L stands for light mode, where, as you remember, the signs don't alternate. Argument P requires to make all elements in sequence positive. The argument is ignored in light mode, where elements must be positive and negative. And argument Q is my favorite, quiet mode. This instructs to print only total durations and errors, if any. The main function uses subfunctions, process int arg, and parse explicit values. Their codes are presented here as well. Variable exit code is initialized with 0 and changes to a positive value in case of an error. Finally, if exit code is 0, we call another function named runner, otherwise we exit with exit code. Now take a look at runner. At start, it defines and initializes some variables, such as range on random data, total durations in nanoseconds for dump and optimized algorithms, as well as error counts, wrong sum if the returned sum is different from the computed sum, algorithm fail if an algorithm returns an error, incompatible range if the ranges returned by dump and optimized algorithms don't match. The exit code is initialized with 0 and changes to a positive number in case of an error. Now the instructions. In case of a light mode, we set positive only to false. If the explicit values are set, we set the number of runs to 1. Otherwise, we need to define the range for random data. For floating point data, this is 0 to 1 for positive only, or -1 to 1 otherwise. For the integer data, it depends on the bit capacity b. In case of positive only, it is from 1 to 2 to the power of b minus 1. Otherwise, it is from -2 to the power of b minus 1 up to 1 less than 2 to the power of b minus 1. Next part of the runner is the main loop, responsible for organizing the runs. At start, we generate the sequence if it is not explicitly specified by calling a randomizer for the range of random data. In non-quiet mode, we print run number and the sequence. There is also an inner loop for two algorithm types, dump and optimized. In the definition of algorithm type, we keep two tables of functions for light and full tasks. As there is a method called function returning the appropriate function. So we record the starting up time in nanoseconds and call the algorithm. If the algorithm fails, we increment the algorithm fail count, set exit code to 4 and proceed to the next iteration of the main loop. Otherwise, we evaluate the duration as the difference between current uptime and starting uptime and proceed. The inner loop continues. The range and the sum are retrieved from the returned algorithm result, and we recompute the sum based on the returned range. If the sums don't match, we print error message, increment wrong sum count, and set exit code to 4. Floating point data may bring inaccuracy in calculations. Therefore, in case of floating point data, instead of requiring the sums to be equal, we check that the absolute value of their difference is less than 10 to the power of -12. As you probably notice, the dump algorithm runs before the optimized one. Therefore, in case of the dump algorithm, we just record the returned range as the dump range, record the duration as dump duration, and accumulate total dump duration. At the end of the optimized algorithm, we in addition need to compare the ranges and durations of the algorithms. So we accumulate the duration as total optimized duration. In case of ranges of dump and optimized algorithm don't match, we print error message, increment incompatible range count, and set exit code to 4. In non-quiet mode, we print the results of both algorithms. We also print the durations of both algorithms and the ratio optimized to dump. In case of C code, we need to free memory for the sequence each time before ending the main loop iteration. You don't see that here because Swift does it automatically. The final part of runner after the main loop ended, and we need to summarize the results. In case of a single run in non-quiet mode, there is no need to print the summary as all the information has already been printed. Therefore, the summary is printed either in quiet mode or if there is more than one run. So we print the total duration for dump and optimized algorithms along with the ratio optimized to dump. In case of more than one run, we also print the average durations for both types of algorithm, and for each error type, we print the count if it is positive. Runner ends with returning the exit code. So let's run. We have here both C and Swift compilation. So let's run, for example, Swift compilation with default parameters. This is convenient for debugging as we see information for each run. If there is an error, we can run the application with explicit values like that. We type, only need quotation marks, we type V, we grab the sequence, we copy, no, what will be? We copy it and we paste it. Oh, again. We copy this and it should work. And we paste it and we close the quotation marks, of course. And here it is. Explicit size is 99 for some reason. Wonder why. Anyway, so we have only one single run because we entered explicit values. Now let's run the same sequence with C. Well, we missed the first element, 118 doesn't appear here. So let's do the same thing with C. Subsec maximum C, V, and we grab starting from 79, where is it here? Copy and paste. And here it is. So with C is even more. Oh, pretty small value. Much faster with C than with Swift. It has probably 10 times faster. I wouldn't expect that. And now let's make it really tough. So this time we make it 1000, make it 5 runs and 1000 elements in the sequence, or maybe 10,000 even. 10,000. And quiet mode, of course. Wow, that was it. 56 microseconds for the optimized mode and 61 milliseconds for the dumb mode in. So it means about 1000 times faster. This is the ratio. Now make it a bit bigger. Make it with C. One round will be enough, but the sequence size will be 250,000. Is it correct? 4 digits. And see how long will it take this time. Remember that this runs both optimized and dumb algorithms, otherwise we wouldn't need to wait at all. By the way, this is Max Mini 7.1, late 2014, dual-core i7 3 GHz. I would like a feedback from recent versions of Mac, because I didn't have chance to test it with recent versions. This is actually a present from someone who wanted me to start developing for iPhone. If not for that, my apps will still run on Android only. What else should I say to keep you awake and not to get asleep myself? Will it end eventually? Yes, it did. 612 microseconds in optimized mode versus 54 seconds in dumb mode. The ratio is 0.00011. And that's the end.